Yes, I think right now it will be same on the YouTube. Yes, and then we will start from now. Yeah, and then there's a but thing showing up, so it's recording now. Okay, so yeah. Hi, if you are watching this sometime in the future. Okay. I already greet you guys. Okay. That's that. Okay, so we talk about the expectation. Now we can talk about the variance, which is another important concept in statistics. Okay, so for the variance, var of x, and this has the formula or the definition for your x deviate from e of x. Here, okay, so now I'm going to use the expectation for now, but sometimes you will also see me using the mu. The mu is also referring to the same expectation regardless of the distribution. So the mu is not necessary for normal distribution. It can also be any distribution, but I'm just referring mu or the e of x as the expectation. Okay, that's one comment I want to mention in case you get confused. Okay, closing the square bracket. Okay, so this is the definition that your expected value, that your x deviate from your expectation. Okay, that's that. And now I'm going to, okay, maybe let me use the mu would be better. I just want to, so here, e of x is equal to mu. Okay, so maybe if I put it this way, it will be more. Okay, so this is what I mentioned earlier. The mu is referring to the e of x regardless of your distribution. And don't forget there's a square. I often forget the square over there, so yes. So the expectation of the x deviate from mu square. I often forget that square, so yes. So if you find out I have a typo, make sure you correct me, yes. Okay, so that is more of a definition for the variance. And then we can also derive a shortcut or a formula from the variance. And then by expanding the terms in the square bracket, in the square term. Okay, so we have the expected value, and then we will have x squared minus 2 mu x plus mu squared. Okay, so here we're just expanding the square and then achieving the second line here. And here the expectation is a linear operation. So that means I can distribute the expectation operation to each of the three terms here. So what I mean by that is the following. So e of x squared. So I distribute the expectation operation to the first term. So e of x squared minus 2 mu ex. So mu here is considered as a constant. So the expectation operation only going to affect on the random variable. And for the second term, the random variable is the x. So I only distribute, so you can only distribute, so you can distribute the e to the x part because 2 mu is a constant here. Similarly, you will have the mu squared. Okay, then we can further expanding the terms, e of x squared minus 2 mu, and then here e of x we define it as mu, so we essentially have a mu squared. So this is the thing I'm going to calling here. I'm going to use this part, e of x equal to mu, so we have a 2 mu squared, and then plus one more copy of mu squared. Okay. Then you will have e of x squared minus one copy of mu squared. You minus 2 copy, adding one more copy back, minus mu squared. Okay, so this essentially gives you another formula for the variance. So the variance of x is also equal to e of x squared, the second moment that we just talked about earlier, minus the square of the first moment. So here the square is outside the parenthesis. So that's also what I was talking about, that the second moment is the variance involving the second moment. Yeah. So this is another formula that you will often see people using to calculate the variance. So one is from the definition that the x deviate from your expectation square. And the other formula that many people use, or in this lecture we will use it very often, is the second moment minus the square of the first moment. So that's another formula. Yeah. Any question? So I'm assuming that you guys have already seen this right before, right? So it'll be, yeah. Okay, so now we are ready to do some examples. Or any question up to this point? Now we're just going to do some examples for particular distributions. Okay, let's do an maybe. So whenever I write EX, this is for like examples. And then also someone was asking about practice problems. So if you can redo this kind of the EX part in the lecture note, that would be a very good, because the material will be very similar to all the EX that you will see in the lecture notes. Okay. Okay, so now our first exercise or examples is that for X following a Poisson distribution. Let me write down the full name. Poisson distribution with a parameter lambda. Okay, can someone tell me what is the support for a Poisson random variable? What is the range for X? Which is a discrete random variable. So what is the support for Poisson random variable? What is the value, the range for the X here? What are the X that the Poisson random variable can do? Yeah.
Greater than or equal to 0.
And then one more thing. Yes. Greater than or equal to 0, yes. Yeah, yeah.
Less than infinity.
Oh, sorry. I thought,
Natural numbers?
oh, sorry. I thought you were talking. Sorry. Yeah. Yeah. So, greater than, you were saying, you said greater than 0.
Greater than 0.
And you said natural number. Yes. So I was also referring that the natural number, not because greater than 0 also involving 0.5, but that might not be right. So
Right.
yes. So natural number including 0. Okay. So that's a very important thing. So 0 is one very important thing that well, I mean, in math, it's already very meaningful. So in our case, yes, 0. So it's a very important value in the support for many distributions. So, and then in terms of the natural number, I really like that answer, including 0. So would be like that. Yeah. So natural number including 0. Yeah. I'm not sure if the definition for natural number including 0 or not.
It is not unless you do n subscript.
Yes.
0.
Yes, so that's why I said natural number including 0. Yes, thanks. Yeah, I often forget the 0. Yes, thanks for the comments. Yes. What is the domain for the parameter lambda?
This is greater than 0.
Yes, thank you. Yeah, you see, I already told that you guys are are experts on this. So yeah. Okay. So anyone still remember, or yeah, if it, well, I was just saying, I was trying to ask if anyone still recall what is the formula for the Poisson distribution, but if you've, yeah, I usually just look up or Google. So let me write down the probability mass function here. So it's e raised to the power of negative lambda, and then lambda. Okay, maybe let me be more precise. So x equal to a particular value k, lowercase value k, where the k fall in the range of 0, 1, 2, 3, natural number including 0. Okay, so the probability mass function for particular x, the random variable equal to a particular realization k, is equal to e raised to the power of lambda, lambda raised to the power of k. The k is referring to your realization for the random variable x, okay, divided by k factorial. So factorial is just like the k minus 1, k all the way including 1. Okay. So that is the probability mass function for the Poisson distribution. Any question up to this point? Okay, so for this exercise, we are going to calculate the following two things. First of all, evaluate, calculate, or whatever you want to call the expectation for a Poisson random variable. The other thing, we want to calculate the variance, which are two very important statistical, let's say, characteristic for random variable distribution. And then here I'm going to use the shortcut, e of x squared minus the e of x, and then the square to calculate the variance. Okay, so here we have the configure or the setup for the problem for this exercise. And then these are the two terms we're going to calculate. Okay, so yeah. I'll just wait for you guys to take some notes. Okay, yeah, so let's first take a work on the expectation of x for the Poisson random variable. Okay, what is the formula for expectation that we just talked about on the top? For the
sum of the beta domain for x times ex.
Yes. So here, let me use. Okay, so then let me use index x here for now. So the support, like you were saying, is starting from 0 to infinity, right? Natural numbers, including 0. So 0 to infinity, but sum over that. Okay, and then applying for the formula. So the random variable x multiplied by the probability mass function. So that is the definition that we just talked about on the top. Okay, so now let's just put down all the components in this formula. So sum of x from 0 to infinity. So the x is just the random variable itself. And then I'm going to bring down this probability mass function to replace the p here. E of negative lambda, and then lambda raised to the power of k, and then k factorial. Okay, so I'm just plugging the term to calculating the expectation. Okay, so here let's just keep reminding. Okay, so in this formula, okay, so here's a typo. Because here I use x, so I'm just going to keep using x, but it's the same thing that x equal to a particular realization. So let me be consistent in the example with the x for now. Yeah, so everything that involving k is just back to x as I use x for the realization here. Okay, so just keep in mind that the random variable is the x. So whatever is not going to be x can be considered as a constant. So for example, you can bring out the e raised to the power of negative lambda in the front. That's a constant term. Okay, and then let's see. The remaining part, they still involving the x. So you will have the first x in the front, and then lambda raised to the power of x factorial. Okay, so the first term here, this one here, that's not involving x, so it's a constant. So I bring it outside the summation. The rest is involving the random variable x that will be affecting by the summation here. So you have the summation for all the x's. So that thing cannot be moving or move any of them outside the summation. Okay. Any thoughts on how we should proceed next on evaluating this infinite summation to calculate the expectation?
Should do some index tricks to get rid of the x in front of lambda to the x over x factorial. So
Yeah, that sounds a very good strategy. What are some other tricks? So you were saying something to remove the x.
yeah, you do that and then you use the Taylor polynomial expansion of e to the x.
Yes, yeah, something like that. Okay, so I think, maybe let me just, sure. I think just to kind of like using a shortcut of what you were describing, so maybe let me introduce one equation for now. So one equation that we can use is that the e of x, so e of x is also referring to the exponential of x if you writing programming language. So this is what I mean. E raised to the power of x is the exp parenthesis x in the coding language. And then one equation for rewriting the e of x is that you can write this as a infinite sum. So this is also equal to k equal to 0 to infinity, and then x raised to the power of k, and then k factorial. This is just an equation, or like a an equation that that we're going to use. That is also another way to applying, like what you were saying, that Taylor series expansion or that kind of things. So let me just use equation to use. Okay, so this is the equation that we know that is equal to the e of x is also equal to a infinite sum. And then you can see that the things that we want to evaluate has something that look like this equation that we can use. So we are going to replace this summation with that to ease our calculation. So that will be our strategy here. Yeah. Does that make sense? Yeah. So this is a known equation, and then this is a known equation. So this is the term that we want to calculate. And then we can see that this part of the equation is very similar to a known equation. So we are going to use or apply this equation, manipulating some terms here, and then to ease our calculation. So that will be our strategy to calculate the expectation. Any question or comments up to this point? Okay, so now let's continue from our quantity of interest, which is this one. So let's see. What are some other things we can do here? Okay, so there's one more thing we can do. Okay. I'm going to call this drop the case for x equal to 0. So if you look at this formula, when x is equal to 0, for one of the x equal to 0, you will see that the first term is also equal to 0. So it does not contribute to this summation, right? So that means this equation is also equal to e of negative lambda summation x equal to 1, because the x equal to 0 case does not contribute any information to this summation. So we can safely write the index x equal to starting from 1. And then still having that. Okay, so from here to here, I'm just dropping the case for x equal to 0. Because if you plug in the first term, the x equal to 0, it does not contribute to this sum. So I can write x equal to 1. Okay, so our goal here, or our strategy here, is to try to manipulate this part of the expression, going to be very close to something that looks like this, so that we can use the e of x to replace the infinite sum. So that will be our strategy here. So now let's think about how we can manipulate this term to make it look like something like this, to be replaced. So that would be our strategy here. Question?
So is it no matter how many like constants you have that you can drop the case for, it will always make x equal 1?
No, the reason, so you were asking why the reason dropping x equal to 0, right? So from here to here, the only change I made is that sign for 1.
Yeah.
Yeah.
So
I-
that has no effect on like
The result.
how many constants without an x there are in the equation.
How many constant of?
So like e to the power of negative lambda, if there was like another variable, like
You mean this part? This part?
Yeah.
This is a constant. It's a fixed number.
Yeah.
So the summation only affecting on x. So whatever we do here is not going to affect the constant.
Yeah.
So we can say we just working on this part, it will not be affecting that. Do I understand your question correctly? Or- Okay. Yeah. Okay. So, yeah, any other question or comments? Or does it make sense? Or if yes,
And the equation to use,
yes.
should the k be x instead? Or like, are the variables?
Oh, this is just like another, let's say this is like a known formula. This is just like a formula. And then we are going to apply this formula to our calculation.
Yeah, no, I'm just saying, because e to the x is obviously written with x, and then the summation is written with k.
Yes, the k is for this one. So you sum over k for n.
Oh, wait.
Yeah,
I'm
so
sorry.
This equation is saying that you sum over this from k to 0 to infinity, you will get the same thing for x, e of x. And then if you think about this, yeah, so consider this just a formula to use or equation to use. And then this is kind of like a, let me use another letter, h of x, like a function for function of x. So you input a function value of x, you can, for example, using a computer, e of x equal to 5, you will get a number. And then if you put 5 on the x, and then k from 0, 1, all the way to infinity, you will get the same answer, this equal to that, equal to this. Yeah. Yeah, good question. Any other question or comments? Yes?
Actually, I'm kind of curious, how exactly does dropping the x equals 0 help us to solving our example?
Let's do it now. Let's do it now. Okay. So let's see what happened next. Okay, so maybe I write it on the second line here. So yeah, maybe it's not that obvious, but let's do some more manipulation on the terms. Okay. E of x, that's the constant. E of lambda, that's the constant part. So right now I'm going to write x equal to, starting from 1 to infinity. Okay, so here we have an x. Denominator is x factorial. So I'm going to write x minus 1 factorial. And then lambda raised to the power of x. Is that okay? I'm just removing whatever, whenever the sum, or whenever the sum happens, just removing one more copy from the denominator. Okay. So again, our goal is to manipulate this part to make it getting closer to look like this. So far, it's still not looking like that. Let's do one more step. The lambda is a constant here. So what we can do, E of that, bring out one more lambda. Summation x equal to 1, lambda x minus 1. Is that okay? I'm bringing the one more copy of the lambda which is a constant outside the summation, so that the power you just have one lambda less. So x minus a 1. X minus a 1 factorial. Is that okay? Yeah. Okay. So now I think we are ready to make the substitution. So what I'm going to do is that I'm going to call j equal to x minus a 1. And then you have the constant e of lambda, 1 lambda here, summation, and then I'm going to use j equal to 0 to infinity, and then lambda raised to the power of j, and then j factorial. So by introducing the j equal to x minus a 1, I'm just replacing the x minus 1 to j, x minus 1 factorial to j factorial, and then x starting from 1, so j starting from 0, because j is x minus 1. And now, the thing that in the summation term here is essentially the same expression as this known equation here. You can see that it's equal to formulation like that. Does that make sense? Or so that would be our, so that's our manipulation to achieve the substitution here. Okay, so maybe let me add one more comment, make the change. So this is equal to e of negative lambda. What is the summation now should equal to? Sorry?
E of j?
E of lambda.
The good question. Let me see. Here's the lambda, and then e of the lambda. Yes. So in this form, applying this formula, in our result, our x is the lambda. So we should write it replaced by e of lambda. Yeah. And then what does this equal to? Just lambda, right? The ex and the e lambda and the e negative lambda cancel. Maybe so. Here is the thing for the. I often forget this one, so maybe let me also write it down. So when you take the product of the two exponential term, is the exponential of the sum inside. So lambda plus negative lambda equal to 1. Yeah. That's I often forget the formula. Yeah. So that they become 1, so that disappear become lambda. So our conclusion up to this point, maybe okay. Our conclusion up to this point is that e of x of the Poisson random variable equal to lambda. Yeah. Any question, comments up to this one? When does this? Oh, okay. So 15 minutes. Okay, good. So I think we are able to finish the second moments. Yeah. Any question up to this point? I hope it's not too boring, or because it's more like a review or for your. Okay, so that's the first moment. So to calculate the variance, I'm going to use this formula to calculate the variance, and then we need. So all we need additionally to calculate is the e of x squared, the second moment. Okay, so this is the thing we want to calculate. E of x squared. Summation again. So apply the formula for the expectation. And then here I'm going to use the index x from 0 to infinity. X square p of x. And then that is just the Poisson distribution. Okay. So let's manipulate this part to get our result. So first of all, let's bring e of lambda to the front. That's a constant term. Summation x equal to 0 to infinity. Okay, so the term remaining is the x squared and then the lambda x over x factorial. Here I'm going to write x squared differently. Okay, I'm going to write x squared in this way. X multiplied by x minus 1 plus x. So this is still just equal to x squared, right? X squared minus x plus x. This is still x squared. Multiplied by lambda x and then x factorial. Right? It does not alter any the value here. But I'm just writing the x squared in another way, as a sum essentially. Yeah. So it does not alter the quantity here. Okay. Next, let's expanding the thing, and later you will see why I write x squared in terms of this. So the first part, the constant summation x multiplied by x minus 1 multiplied by lambda x factorial. So I'm just taking the first part in the square bracket plus the same thing that involving the second term in the square bracket. Okay, so do you agree with that? I'm just distributing the terms to separating the square bracket to get these. Okay, so now let me ask you a question. What is the second term here equal to? Does it look familiar here?
Oh, it's equal to e of x.
Yes, exactly. This is just e of x. This is just lambda. We don't need to work on that anymore. That's the reason why we make the square bracket here, this expression. So we remove one part of the equation. Oh, we already have the answer for that. So that's the trick. Okay, so now we just need to focusing on the first term. And then we're just going to apply the same tricks again. Like removing the factorial and then change the index and then you will get the answer. Okay, so now I'm going to write e of negative lambda summation. Let's see. Is it okay if I skip some steps or?
Yeah.
Okay, so the same trick again. It just so I'm not going to write down the thing. So at lambda square, I'm going to bring 2 lambda from the numerator, so the numerator will become x minus 2. Okay, and that also means the x starting from 2 to infinity, and then lambda x minus 2. So I'm borrowing 2 more copy from the numerator, so it becomes to the front, divided by x minus 2 factorial. So I'm just applying the same trick, kind of like applying twice to bring 2 more copies, changing the index for the summation, and then changing a term here, right? And then now we call j, introduce another j, equal to x minus 2. That means e of negative lambda, lambda square, j equal to 0 to infinity. Oh, okay. Don't forget there's another lambda here. That's the second part. We already know the answer, but just make it complete. Yeah. And then let's see. Lambda raised to the power of j factorial. Okay, make a comment here, make the change to the e of lambda. Yeah, don't forget there's a plus lambda from here. Okay, e of that lambda square, e of positive lambda plus lambda. So the final answer for the second moment is lambda square plus lambda. So just to remind you, this is the second moment for the Poisson random variable. Okay, so now we are ready. Oh, any question up to this point? Or maybe I can pause a little bit for you to finish up the notes. Yeah. Any question, comments, or any thoughts on any tricks that we use? So we finished calculating the first moment and the second moment. Now we're ready to calculate the variance. Okay, so the variance of x equal to the second moment minus the square of the first moment. Plug in the terms that we just obtained. Lambda square plus lambda minus lambda. Don't forget the square for the square of the first moment. That is the lambda, variance of x. So this, you've probably already known all these results. For Poisson random variable, the expectation is equal to the variance equal to the lambda, which is the parameter of the distribution. Okay, yeah. So I think there are just 5 more minutes. Maybe I will not talk about the exponential example. I will stop here. So yeah, I will stop today's lecture at